Hello! In this tutorial I will show you how you can get audio data from a WAV file inside of Blender using Python. And then we will also have a look at a very simple example of doing audio visualization using geometry nodes. You can also do this with a plugin I just released. You can get it on Gumroad. Link will be in the description. And also, of course, I will show all of the relevant code, just missing some quality of life features in this video so you can build it yourself if you want to. Of course, this is a very basic example. You can also do complex stuff, like here's an example where I use the audio data as input to drive a particle system, and then I get something like when you put sand on a speaker and play sound. But I think this, what I'm showing in this video, is a great starting point. You will understand all of the basic parts that go into it, and then you can build on it by yourself. I hope you have fun. So here we are inside our fresh Blender file, and using the Waveform plugin, all I need to do is hit N to extend the sidebar, and then we see here on the bottom there's a tab called Waveform. I click it, and then on the top you already see wave path. So this will be the path to our file that we want to use for visualization. Just clicking the folder, it opens the file browser and we can just navigate to the file we want. Keep in mind, this will only work for PCM integer encoded WAV files without compression. It could be 8, 16 and 32-bit, that's all fine. Just it needs to be a PCM integer. So I'm picking this Eversense track here. You can find the link to it in the description. And I hit accept to then actually display and generate the waveform mesh. All I need to do is hit update. And here you can already see it. So now if I hit play, yeah, the song is a little bit quiet in the beginning, so there's not so much motion. But just scrubbing ahead a little bit, here you can see now we get the proper motion that we expect. And also, as you can hear, we already get a real-time preview of the sound that is synchronized with the visualization. This is because it automatically also adds. Let me open the sequencer quickly. Yeah, here in the sequencer you can see it just adds this pink audio track that is a mirror of the file that we basically link here for our file path for the waveform mesh. And that's that. That's how simple it is. Also, if you're interested in that, you can use a spectrogram representation. So this shows more like the individual frequencies at this point of the track rather than the raw waveform. And another thing you can do is just adjust the number of samples you want to have for your track. This is just an arbitrary value that you can pick however you enjoy it. Yeah, that's it. So I just want to go over the code rather quickly. There will be another video on my channel where I go over every line in detail for people who are not experienced with Python programming or like scripting inside of Blender at all. But this is the fast version, so keep that in mind. So big picture, what are we doing? We are using a module that is included in every Python distribution, so you don't need to install it. It is called WAV. This allows us to open WAV, like WAV files, and we can just extract the data. What we want to do is, of course, we want to get all of this data from our relevant WAV file, and then we want to pick a section of relevant data for each frame and display it in the form of just some displaced vertices of a mesh. Of course, we need some file path to get the WAV file initially. And here we do wave.open and RB is for read. And of course, we make sure to put our R in front of the string, so it's a raw string, or we invert our double slashes if we are on Windows. Here we just get all of the formatting information of the WAV file because it could be many different formats. This script only supports PCM integer WAV format and also no compression, but still it could be 8-bit, 16-bit, 32-bit, 24-bit also, but we don't support it. Yes. Then, yeah, we open our file, we just store the whole byte array in one variable, and then we close the WAV file again. Then we have this little case statement here, just to make sure when we do the conversion of the byte stream to integer array, we do it in the correct format. So it could be unsigned integer 8-bit, or it could be signed integer either 16 or 32-bit. Awesome, yeah, I just put it all in the same variable as you can see. And then we also got the channels earlier from the file, and now we just use it to make sure if we have a stereo file, we kick out every second value of the array. Then we're already at the animate function. This is the function we want to run every frame, and it will do the actual animation of the mesh. First, we are checking for an object that is called waveform. You could create it in code. I didn't, so this is just assuming there is already a mesh with this name, or it will not run. And yeah, then we are storing it in a variable sample length. So this is, since audio has a higher number of frames or has a higher frame rate than video, we want to pick many audio frames to display on our mesh for a single video frame, since also a single audio frame is just a number, and then we don't have any wave shapes at all. So I'm just arbitrarily picking 1024. Then we want to know, yeah, here we're just converting the frame, the current frame of the scene, to an actual time in seconds. So then we can later use this here together with the waveform rate. So this is the, here I assigned just the basically frame rate of the audio file, of the WAV file. We multiply it by our time in seconds, and then this gives us the index of the frame from our audio file we want to pick. So this is the starting of the samples we want to, of the sample section we want to get, and then the end will just be adding this 2024 to the index that we got when we scaled it with the time. Yeah, and then we just have this new array, which is like this spliced array between those two indices. Just creating some empty arrays for vertices and edges so we can fill them with our nice data. And we have the bit depth scale. This is actually quite crucial. I got confused about this today before recording this. Since we are only using integer format, if the audio file has higher precision, this also means if we just get the raw integer data, well, for 32-bit files we get higher integers than in a 8-bit file. And if you don't account for this, you will just have like messed up scaling between different files. And since it's like a factor of like 100 million, it will just look like a confusing mess and will even look like it's not working. So that's how I got confused today. Yeah, when we have this, we are completely equipped to just run through, like enumerate through our array of sample data and just convert the index into our X possession of our vertex. And then for Y we get 0, and for Z we want then actually the value that is contained at this index divided by our bit depth scale. So it is normalized. And in the end, I'm just connecting all of the vertices with edges. You don't need to do it, obviously, clearing the geometry and putting the fresh vertices and edges into our object. Yeah, and all of this is appended to the frame change pre-handler. And before this, I'm just making sure to clear anything that might still be in the handler to make sure we don't get stacking. Like, we don't have old versions of our functions still stuck and being executed every frame, because that would be very confusing. So important parts: use the wave module, make sure you do correct conversion of bytes to integers, considering the format of your WAV file, cut out the channels you don't want, and then take a small section of this data, considering the timing, like the frame of your scene. And you can do this by just attaching a function to the frame change pre-handler. That's it. So now we have our waveform mesh, and no matter what kind of effect or visualization we want to create, first step is to create a new mesh. And then we go to the Geometry Nodes tab, where I already am, luckily. What a coincidence. And I just create a new Geometry Nodes setup. It automatically adds the modifier to my mesh. And then I take this waveform mesh from the outliner and just drag and drop it over here. Then I plug this geometry into our output, and we see the cube disappears. And basically what we just did is we created an exact copy of the waveform mesh. So if I hide it now, you can see it still looks the same. If I hide the cube also now, you can see it's actually the cube. So cube is now just a copy of the waveform mesh, but inside of geometry nodes. So we can access the data freely. What I want to do now is just go over this little node setup that I have prepared step by step, and we can just enable every part by itself and see what's happening. Also, there is some surprise here. I'm disabling it for now, and at the end, this is a small bonus. I think it's quite cool and a simple thing to do. So first two steps are really simple. I'm just removing the edges. So you can see here, we have this connected line, and then I use the delete geometry node. I set it to edges, and I set it to only edges and faces, because otherwise it would still be deleting the vertices that are connected to these edges. Yeah, but now if we set it to only edges and faces, we turn our mesh into a collection of points. And second one is just simply to do some scaling. Just transform geometry so we can do some scaling of the amplitude of our waveform visualization. Next step is reducing the number of points. So you can see we have many points. And specifically for this example with the moving bars, it's just too many points. I don't want to use all of them. So I used delete geometry, but since I don't want to delete everything, I need to make some selection here, what I want to delete. And for this, I'm using the modulo operator. So modulo, what it does, it just gives us the remainder of a division of two integers. So if I, for example, input 5 and divide it by 3, then I would get 1 with the remainder 2. If I input 6, then I get 2 with the remainder 0, because it perfectly divides by 3. So what this means is we have our index, which is just the numbering of our vertices. And we have an integer that is this is the number we divide by. So this basically means for every number of integer that's not perfectly divisible by this number, it will be deleted. So if we set it to 2, we will delete every second vertex. If we set it to 3, we will only keep every third. If we set it to 4, only every fourth, and so on. So let's set it back to 8, and we get a reduced version of the mesh that still has the same shape. Then it's already time to extrude the mesh. So we start forming our bars. You can see it basically it's almost the full effect, just without thickness. How I do the extrusion is basically, let's go back to before the extrusion. So you can see these points here, they are flying on top, like above the 0 line. And then I just extrude them down to 0. The way I do this is I take the position input and then I multiply it with a vector math node, just multiplying everything by 0 because I don't care about the x position, about the y position. I only want the z position, but then I want to invert it. So for example, if our point is at +1, I want to do an extrusion by -1. And that's how all of these lines then connect perfectly to the 0 line. So even if we are on the bottom, it would be a position of -1, and then we multiply it by -1, so it would extrude by 1, which is then going up, and it also ends up being 0. Then basically the only thing that's missing in terms of shape is the thickness. And the way we do this is we just do a conversion from mesh to curve. This does basically nothing. You can see it still looks the same. But what this allows us to do is we can do a curve to mesh, and the curve to mesh node takes also some profile curve, and this will be the thickness. So here I'm just inputting a curved circle. Could also be any other shape if you want to make your bars in some other form. And I just set it really low. I set it to 4. Maybe even setting it to 3 is fine. But yeah, this way, since we only see it from the front, you can't even tell if it's round or not. So it doesn't really matter. And yeah, that's how we get our thickness. Now to the most fun part. We can tell it's fun because it's yellow. It is the material. So if I show the material preview here, you can see we have some transition going on. It's not just a single color, and it starts really bright at the bottom or like at the starting point of each bar, and then it fades out, gets dark to the top. And what we need to do this, we need some value that we can access inside of the material that basically is a high value, or that is one value for the bottom and one value for the top. And the way to do this is just use a store named attribute node. So you can see here I'm storing an attribute. I say it's a float at face corner. I think this is important. If I do point, no, if I do point it still works. Okay, it's not so important. Yeah, I just name it tip, I store a float, that's everything. And if I go over to the shader, let me just pick it here quickly. It's this material. We can see I take an attribute node which then references the same name that I gave in geometry nodes. And also we need to decide, so if we do it like this, it just assigns the same value to all of the vertices it gets. So we need to decide what vertex needs what value. The way I'm doing this here is I just take the position, or basically the goal is I want everything with a Z position of 0 to be bright and everything that is not 0 to be dark. That's the whole story. And achieving this is quite simple. So I just take the position, I isolate with the separate XYZ, I isolate the Z value, then I'm using absolute because we could get from this node negative or positive Z position. And I want to make sure they are only positive. So this is what happens after this node, only positive values. And then I'm simply checking, is this value that we have greater than 0 or is it 0? And I'm inputting this to the switch. And what this switch does, let me disconnect it so you can see it. So if I check this box, it just says, if I get true here, I will pick the bottom value. If I get false, I will pick the top value. And since we are having this input here that says, is this position 0 on the Z-axis or is it something else? We have this to separate basically if it should be bright or dark, and we get this nice fade. For completeness, let's also have a look at the actual material. So I showed a little bit of it earlier, but what's happening here basically is we just have this attribute node. You can find it by just searching for attribute, and then you want to input the same name that we assigned in geometry nodes. So I just go over here, I hover over the field, over the name field, and push Ctrl Z, Ctrl C, I guess. And then I go over here, Ctrl V. So I copied it over just to make sure that it's actually the same value. And we don't get any trouble because of this. Yeah, and then here I just have a mix color node. If I don't use the input, then I get this slider. If I slide it to 0, we get all the way black, so the color we assigned to A. And if I slide it to 1, we get the color we assigned to B. And using this property, we can just input our value, and then we get this transition because the input factor will be different for the top and the bottom of each bar. And I just added this invert node here because I wanted to have the option of flipping this gradient. Yeah, and then the color just goes into the color input of an emission shader, and that's the whole material. So very simple. So now for the bonus, let's just play this. So this is the result we got. And if I unmute this section here, then you can see, of course, it mirrors, but also we get some different motion. It's not just jittering around, it has some more weight to it. So mirroring without the weight, it would move like this, but everything is slowed down and has a little bit more calmer motion. The way this works, if I just take a fresh geometry node tree, and we have this basic thing again, we just input our waveform mesh into the output, and it's a mirror of the original mesh again. Easy, easy. But see what happens if I put a simulation zone between it. Just inputting our mesh and outputting it after the simulation zone. But you can see, even if I play it, the mesh doesn't change anymore. But now if I do in the middle of the simulation zone, if I do something, let's just join geometry. And then I join in the new geometry. And now you can see we get the changing geometry again. Let's pause it before my computer dies. Yeah, I love this because already the possibilities just go phew. But yeah, this is the concept I applied in this other node tree. So going in here, you can see I'm using a set position node, and I'm mixing this position out of two values. One of them is just the original position. So as you can imagine, if I just input this again, nothing happens. And the other one is then, let's ignore this whole mix thing. Yes, the other one is just sampling the index of our geometry, but crucially before it goes into the simulation zone. So what we get here will still be just the copy of the waveform mesh before it goes into the simulation zone. And then we are taking with sample index position, we are just taking the position of this, so the position that's updating every frame. So we could also just set the position to this. And you see it's the same behavior. So now you can imagine what's happening with the mix node. So I'm taking the one position that's always updated. I'm taking the one position that always... No, it doesn't stay the same, but it is basically the current position of the mesh that is actually rendered. So if I slide this, 0 will be just no motion, 1 will be all of the motion all the time. But then what happens if I go to some low value? Now we are mixing the position where the updated mesh is and the position where the rendered mesh is. And we're just blending, but we're adding just a tiny hint of the motion every time, so it moves quite a bit slower. And then also you can see this more complicated switch setup. But it is not so complicated. I'm just checking, is the position where it should be higher than where it is? And in this case, I will just use 100% motion. And in the other case, I will use softened motion. So this means if our bar should be at a higher position than it currently is, it will move instantly. And if it is at a higher position than it should be, then it will just go down softly, gradually. And now when I play it again, yeah, we get this beautiful behavior where the bars just shoot up, but then they descend slowly. And that's it for this tutorial. I hope you had fun. If you have any questions, please ask them. I'm happy to talk to anyone who is interested in this stuff. And if you consider picking up my plugin, thank you very much. It helps me out a lot.